Hi, I am Nusret and I will be talking about our paper, Goldfish, No More Attacks on Ethereum. This is joint work with Francesco D'Amato, Joachim Noy, and David Shea. Ethereum's long-awaited merge, the switch from proof-of-work to a proof-of-stake consensus protocol, happened in September 2022, ushering in the era of proof-of-stake consensus. But is this protocol secure? The basic version of the protocol, known under the name Gasper, was described in this archive preprint from May 2022. However, the protocol was quickly found to be vulnerable to various balancing and other low-cost attacks. These attacks show that the protocol not only lacks liveness and safety, even against low-stake adversaries, but is also vulnerable to reorgs, where honest blocks are displaced from the chain. In fact, a version of these attacks was presented in this very same conference 2 years ago. In response, a patch called Proposer Boosting was implemented. However, this patch also falls short of securing the protocol, as was evidenced by future attacks. In response, another patch called Equivocation Discounting was implemented. Now, the protocol at the time of the merge was simply Gasper, added layered with these new patches. However, this protocol lacks a security proof. All of the attacks we have seen so far concern a particular component of the protocol of Gasper, for which we propose a drop-in replacement that is called Goldfish, and we show that a variant of Gasper with Goldfish is secure via security proofs. Let's take a closer look at Ethereum Consensus. The consensus protocol consists of two sub-protocols. LMD Ghost takes transactions and outputs the chain tip, whereas Casper FFG checkpoints blocks on this chain and outputs a finalized prefix. These checkpoints, in turn, influence the workings of LMD Ghost. The requirement for the chain tip is to remain safe and live under synchrony and unexpected temporary crash faults that might affect a large portion of the validator set. The finalized prefix should always remain a prefix of the chain tip. If you would like to learn more about the desiderata for these two ledgers, you can check out this paper. We have seen that LMD Ghost here is not secure. Moreover, the problems with LMD Ghost affect the whole protocol. Indeed, if LMD Ghost is not live, then we have no hope of making progress in the later portions of the protocol. Similarly, if LMD Ghost is not safe, then validators cannot agree on which blocks to checkpoint, implying that the finalizations would stop. Now, one proposal here would be to replace LMD Ghost with a protocol that is known to be provably secure, such as Nakamoto Consensus. Nakamoto Consensus satisfies the desiderata for the chain, which is to remain secure under synchrony and many temporary crash faults. These requirements are also known by the name sleepy model. Nakamoto Consensus is also communication efficient. However, it is not reorg resilient, as was shown by the selfish mining attacks. It also suffers from a slow confirmation due to its K-deep confirmation rule. Now, we propose Goldfish as a drop-in replacement for this box, which was occupied by LMD Ghost. Goldfish remains secure under synchrony and many temporary crash faults, and it's also communication efficient. Moreover, it satisfies reorg resilience by ensuring that honest proposals cannot be displaced from the chain. It can also support fast confirmations, and it's quite similar to LMD Ghost. This similarity of Goldfish to LMD Ghost gives it a credible path to adoption, as it minimizes the amount of change that needs to be done to replace LMD Ghost with Goldfish here. To understand how Goldfish avoids the pitfalls of LMD Ghost, let's take a closer look at it. We consider the sleepy model with delta delay bound on network delay, unexpected temporary crash faults, and an assumption of honest majority amongst the remaining validators that remain awake. LMD Ghost proceeds in slots of length 2 delta. Each slot has 2 randomly selected roles, 1 block proposer, and multiple committee members or voters. At the beginning of the slot, the proposer runs the fork choice rule and proposes a block extending the identified chain tip. For this purpose, it inspects the tree of blocks in its view, as well as the latest unique votes by the validators on these blocks. It runs the ghost greedy heaviest observed subtree fork choice rule. The fork choice rule starts at the genesis block, and at each block, it inspects the subtrees rooted at the children of the block. It then selects the subtree with the largest number of these unique latest votes, in this example, the left subtree, and moves to that left child. This process is repeated until the fork choice rule identifies the chain tip, which is a leaf block. At this point, the proposer extends the chain tip with its new block. Delta times into a slot, the voters run the same fork choice rule and cast their votes for the identified chain tip. In this example, they will, upon running the same fork choice rule, they will identify the proposal of the proposer, namely this block 5, as the chain tip, and they will all vote for it. We now show how the adversary can sway the honest voters into not voting for a block that conflicts with the proposal. For this purpose, let's consider the example from the previous slide. Let's suppose that the adversary has 2 votes from slot T-1 that he has not shown to anyone yet. It then shows these 2 adversarial votes from slot T-1 to half of the honest voters of slot T before the voting time of slot T. As a result, the honest voters that do not see these adversarial votes from slot T-1 would identify this left subtree as the heavier subtree, whereas the honest voters that observe these 2 adversarial votes before the voting time of slot T would identify the right subtree as the heavier subtree. As a result, honest voters would be split as to which block is the chain tip. Now, this means that they will vote for conflicting blocks. Now, once delta more time passes, all honest voters observe these 2 adversarial votes, it will be evident that this block 4, which conflicts with the proposal, is the chain tip. Now, this is bad because this implies a reorg, namely, this honest proposal is no longer part of the chain. Moreover, this technique of swaying votes, seen here in the simple case of reorging a single honest proposal, which is block 5, can be used to build full safety and liveness attacks. This brings us to Goldfish. Just like LMD Goldfish proceeds in slots, but this time of length 3 delta. As in LMD Ghost, every slot has a proposer and a voter committee, selected with probability that's in proportion to the stake owned by these validators. Just like in LMD Ghost, every voter or validator maintains a tree of blocks and votes called the block vote tree. However, unlike in LMD Ghost, now every validator also has a buffer. Whenever validators receive a new message, these messages do not go into the block vote tree immediately, but instead they are received into the buffer. The validators run the same fork choice rule ghost on the block vote trees. The magic sauce of Goldfish is how and when these votes and blocks are added from the buffer to the block vote tree and can later be removed. This process of adding and removing votes is guided by 2 principles. The first one is vote buffering, also known by the name view merge, and the second one is vote expiry. At the beginning of each slot, the slot proposer adds the messages within its buffer to its block vote tree. It then runs the ghost fork choice rule on the block vote tree by using only the slot T-1 votes, identifies a chain tip, and extends it with a new block. It then proposes the whole block vote tree, including the new block, as its proposal. Now, delta times into a slot. Upon receiving a proposal, the voters add the messages within the proposed block vote tree to their local block vote trees. They then run the same ghost fork choice rule, again using only the slot T-1 votes in that block vote tree. Then they identify the chain tip and vote for it. Finally, 2 delta times into a slot, every validator adds the messages within their buffer to their block vote tree. Finally, Goldfish confirmation rule outputs a block and its prefix as the confirmed ledger. Once the block becomes T confirm time old and is still on the ghost tip according to the non-expired votes. Here, T confirms a parameter that is selected to be sufficiently long. We next show security. We will show security by virtue of first showing reorg resilience. Then we will bootstrap safety and liveness from reorg resilience. More formally, we first show that a block proposed at a slot T with an honest proposer is part of the ghost chain at all future slots, starting at slot T. Our proof will be by induction. We will first show the base case, namely, if the proposer is honest, then all slot T honest voters vote for the proposal. This will follow from vote buffering. Then we will show the inductive step, namely, if all slot T-1 honest voters vote into the subtree rooted at B, then all slot T honest voters vote into the subtree rooted at the block B. And this would follow from vote expiry. Together with the base case, inductive step shows that all honest voters starting at slot T either vote for block B or a subtree rooted at block B, implying that the B will stay as part of the chain at all future slots. Let's first show the base case. For this purpose, let's consider a time horizon. We are now at this time that is delta before the beginning of slot T. Here, we observe the views of 3 different honest validators at this time. Now, suppose the adversary shows 2 adversarial slot T-1 votes to the leftmost honest validator here. At this point, these votes are in the buffer of this validator, and they are not yet added to the block vote tree. Once the validator adds the message in its buffer to its block vote tree, these 2 adversarial votes appear as part of its block vote tree. At this point, the honest validators disagree on which block is the chain tip. Now, once delta more time passes, these 2 adversarial votes from slot T-1 are observed by all honest validators. This is because the honest validator here on the left side, upon receiving them, would broadcast it to all other honest validators. However, just like as was in the beginning, these 2 adversarial votes are received into the buffer of the other validators. Here we see the 2 adversarial votes at the buffer. Moreover, there would not be any updates to the block vote trees of the honest validators until the voting time of slot T here. As a result, these 2 adversarial votes would remain in the buffer. Well, this is true unless we consider the proposer of slot T. Now, observe that the proposer adds the message in its buffer to its block vote tree before identifying a chain tip and extending it with a new block. As a result, these 2 adversarial votes will be added to the block vote tree of the proposer. Now, proposer runs the fork choice rule, extends it with its new block. Note that the proposer's block vote tree is a superset of the block vote trees of all honest validators. Now, delta more time passes, the proposer proposes this block vote tree, all honest validators receive it, they add the proposed block vote tree to their local block vote tree, and they obtain the exact same block vote tree that was proposed. This is by the virtue of the fact that the block vote tree was a superset of all local trees. As a result, all honest validators and voters, they would identify this block tree that was added by the proposer as the proposal as the chain tip, and they will all vote for it. This basically proves that if the proposer is honest, then all slot T honest voters would vote for its proposal. We next show the inductive step. Suppose all slot T-1 honest voters voted into the subtree rooted at the block B. Here we see the subtree where all honest slot T-1 honest voters voted for. Here are all the votes. And now let's consider a conflicting subtree shown in blue here. Note that the voting rule requires the chain tip to be identified only looking at the slot T-1 votes, and that was by vote expiry. Moreover, all slot T-1 votes by honest validators went into this subtree, and by our assumptions, there are more honest voters in each slot than adversarial voters. This implies that in the fork choice rule, this purple subtree here, rooted at block B, would be heavier than any other conflicting subtree. And as a result, all slot T honest voters would identify a block in this purple subtree as a chain tip, and all honest votes in slot T would go into the subtree rooted at B. This basically concludes our inductive step. We have thus far shown that reorg resilience, that a block B proposed at a slot with an honest proposer would remain part of the ghost chain at all future slots. Let's now show how we can bootstrap security from reorg resilience. We'll prove that Goldfish remains safe and live. For this purpose, we will first observe that within each T-confirm period, for a T-confirm selected to be sufficiently long, there is an honest proposal with high probability. From reorg resilience, we know that honest proposals are eventually confirmed with the same prefix as determined at the time of the proposal. And as a result, honest proposals stabilize their prefix, and they include new transactions by the virtue of being honest proposals. And because now there is an honest proposal within each T-confirm period, the chain will be stabilized and would include new transactions, thus proving Goldfish safety and liveness. I've shown that Goldfish is safe and live under synchrony and temporary crash faults, namely under the sleepy model. It is reorg resilient and is similar to LMD Ghost. You can check out our paper at this QR code for more details on the composability of our protocol with accountability gadgets, fast confirmations under high participation, and its communication efficiency given subsampling of the voter committees. In the paper, we also report on an efficient implementation of the protocol. In the protocol I have described, you may have observed that the proposer sends out the whole block vote tree in its view. You may object that this is horribly inefficient in practice. However, there is a way to represent these block vote trees in a very succinct manner so that they are constant size, thus making our protocols practically efficient, and we show that in the paper. Finally, if you have been following Ethereum, you know that there are now proposals for consensus upgrades discussed under the name single slot finality. And if you take a look at these, you can find Goldfish in there. Thank you.